Today we will discuss the shear. You know what is a shear is? When a force acts along a material at a particular angle apart from the principal axis, then we call the effect caused by these forces is a shear effect, right? So shear, if we consider a material, right, the two principal axes are this. So if any force act this way with an angle, then we call, let's say, effect shear. And shear mostly cause a rotational effect, right? So shear, there are two type of shears. One is a pure shear, the other one is a simple shear, right? You know the basic shear. Let's take a bunch of cards. If I just apply, the bottom one is fixed, the upper one, if I push it, then it will make some kind of effect. This property we call it's a shear. So if you look into this effect we called a simple shear. So simple shear, how it looks, we have a shear here, the bottom one is fixed, the upper one I just apply a force, so it will change the dimension with an angle theta. We call it shear. The shear strain gamma equal to tan theta, right? There is another type of shear also, we called here pure shear, right? So the pure shear strain, uniform deformation of body by uniform tension in one direction and contraction in the other direction, so the area remains constant. So this is a simple shear. The other one is, let's take a fabric. It's a square shape, right? If I just pull this portion, what will happen? It will change the direction to this way. Right? A dash, B dash, A dash, D dash. So what happens if this occurs, the principal direction, the angle remains same, the area will be same, right? In pure shear, the area of the original dimension and the area of the deformed mass will be same. But in case of the simple shear, the area of the original shape and area of the deformed will be different because there is an angle occurs. But here there is similar extension. This is a contraction their side, and here there is a extension. So the contraction and extension will be same. That we call the pure shear, right? So here we consider this is a pure shear. There is a contraction. The original size is L0. Now the contraction is small e, so that will become L0 1 plus epsilon. Similarly, the contraction in the width wise L0 by 1 plus e. If both are same, so increase in width L dash 0 is equal to L0 plus 1 plus e. Reduction in width L0 dash is equal to L0 by 1 plus e, and where 1 plus e is equal to L0 by L dash. So here if we multiply the area, because both are area width L0 1 plus e into L0 1 by e 1 by e cancel, so L0 square, that will be the same, the area will be remain same, but there is a change occur, the angle here, the angle theta, but the angle may not be remain same. So what is the change of angle? If this is alpha, the change of angle, one is pi by 2 plus 2 alpha, the other one is pi by 2 minus 2 alpha, right? So now what are the problems occurs in case of the shear measurement? How we can define the shear measurement? Shear, one practical problem we faced during the fabric shear, because when we apply a force in a direction not in the principal directions, then the deformation we called is a shear deformation. Here when we apply a force, there is a effect of buckling. So what is buckling? If I just push this one, what will happen? It will bend at its original position, right? So this effect we called a buckling. Then there is a ununiform stress distribution due to tilting of the lower clamp. That's why there are some practical problems. So Taylor devised a method to determine the shear method. So he take two clamps, one lower clamp, upper clamp. They are all connected with some ends, right? Now this was connected with the hanging mass, and here there is a mass. So when it is mass is works, so the first one is moves this way, but this one is fixed. The upper clamp is fixed, so the lower clamp moves out. So here there is some kind of shear. So now previously it is this way, now it is become this way. The angle become theta here. So there is a weight W, the displacement is dx, and the horizontal direction dy. So W is equal to mg. So if you resolve this component, tan theta is equal to f by w, or f is equal to w tan theta. That is f. This is w in this direction. This is the weight. This is the force in the thread axis, because they both are connected. Alright. So work done is equal to f into dx. The displacement in the along the y, work done is a change in potential energy, which is equal to w dy. So work done in the shearing force is equal to f dx minus w dy. So this way effective shear force we can get S is equal to f minus w tan theta. What is tan theta? dy by dx. It's very simple. So this is a method used trailers to determine the shear. But there is another problem in shear, which we call the shear hysteresis. What is a hysteresis? If we make a curve, this is like an alternating current. If we deform it, it will move this way. After the yield point, it will maybe move this point. If we remove the force, it will never return to this original position. If it will return, then we call it a pure elastic material. Beyond the yield point, it will never return, so it will return to this position, right? Now if I apply, let's say stretching it, I will compress it, so it will move this way. In the opposite direction, I have applied a force. We got the extension same, but the work done will be higher, so it will come down this way. Again I apply a force, so we call it hysteresis. Hysteresis means, we called, what is a hysteresis? When we apply a force, it will never return to its original position. To return to its original position, I applied in the opposite direction. When I applied the opposite direction, I got it here. This is the recovery. Again I forced to recover to this original point, but I never reached to this point O, right? So I reached instead of here. Again I applied in the opposite direction of this force, the original direction. Here I reached here. Again I come to this point, but never I reach to this point. So hysteresis is the loss of energy during the movement, and we cannot reach to the original point, that we call the hysteresis. Similarly, shear is a hysteresis problem, so we call this shear hysteresis. Here, what is the x-axis? This is the shearing angle. What is the in the y-axis shearing couple. What is couple? Couple is force into displacement. So where we applying the force? Here to original position, it will reach to this position. This is the original or the yield point or the proportionality limit. It will reach to the B. Here buckling occurs and I return to this original position. Here I never reach to this position, so I reach here. Then D, I return to this point A and here. So this is called the here shear hysteresis curve. What are the different point I can get here? Initial shear modulus, slope at the origin, right? Then shear modulus, which is called the G, the shear stress divided the shear strain. Force by area, delta x by L or FL by A delta x. So this will be gram weight per centimeter square per degree. Right. There is a model also used to explain the one analogous model is used for the explanation of shear. So shear hysteresis. Here we have taken two springs, in between there is a block is present and the block is present on a surface, right? So when a force is applied at this point, what will occur? The spring 1, this is the spring 1, this is the block, this is the spring 2, this is attached to a fixed surface. So T1, T2 and the spring constant is capital E1, capital F2, sorry E2. So what will happen? If I just push this side to the free end, the spring 1 will expand until it will reach the frictional coefficient of this block. What is the frictional coefficient? Mu into N or mu mg, right? So when you exceeds this mu mg, then the block moves. When the block moves, the strain or the spring get extended, right? So we can say where the first stressed AB. Now if I release this one, so spring 1 is first is exposed or extended, the second block, the block is again moved. If I remove without this one, it will return to its original position. There will be sources. This called the extension of the first method, right? So this is OA. OA represents the extension of the spring 1. Now when 1 is extended enough and the frictional coefficient or the frictional force is overcome, then the spring 1 will be stressed as well as the block 1 will move in this direction, and this experienced in AB. Now this AB, when this moves, the spring 2 is also going to extend. That is mentioned in AB. Now if I release, it will return to this original position, and the same way it must overcome the frictional coefficient, it will move, and we can get this hysteresis curve. That means it will never come to the original position. Let's compare it with a fabric. Now fabric, this is the warp, this is the red one is weft. So we have this free length, this is the bounded length. So if I just apply the force, it will change in this direction. First as I told you earlier, there will be the breaking of this frictional point. So this is explained by a block. So first one is this one is the spring 1, and this middle one is this is the block, and this is the spring, explains the spring 2. So if I will just pull this here, what will happen? It will extend, and if the frictional coefficient is overcome, then the spring 2 will be allowed to extend, right? So this is the analogous model, and the explanations are written here. You can read it, what will happen. Thank you.